the procedure to make an answer to the following questions. How many qubits are required to solve a certain problem, and how long it takes to solve the problem with those qubits? And so far, several researchers have estimated that based on the quantum computation core components, such as algorithm, quantum algorithm, and error correction and hardware, there are several reports about them, performance and research. In 2010, Professor Lowe defined the quantum computation time is the multiplication of error depth and error learning time. So by their calculation, 409 days are required for sure 2084. And 2 years later, almost the same guys improved the error, so the learning time is decreased to 180 hours from 400 days. And the same year, Austin Fowler separately defined the quantum computation time is the T-gate depth and T-gate time. So the time is reduced, dramatically reduced to 27 hours. And 9 years later, Gidney defined for sure algorithm, quantum computation time is modular expression, exponential depth and modular exponential time. So they say 8 hours is enough for breaking RSA to 2008. But I totally agree with the complexity analysis is very important. But I cannot agree with the data because I think we cannot experience such quantum computation of such performance in real world because so many things are omitted in the complexity analysis, such as something determined dynamically. So in our work, we want to make some data that is very much, as much as close to the real world. Okay, so this is, let's go to our proposal. We have thought about that if we can make this kind of a circuit of entire quantum computation, then it is possible to make real data as much as close to the real world. So we guess we take an approach like this one. First, make this kind of a circuit and trace all the operations for learning algorithm, then we can find some data. For that, we assume the left side also. Left side some architecture for universal quantum computation from the user layer to the device layer. And based on the architecture, we progress the analysis like this sequence. In the beginning, we compile the algorithm into the list of all the quantum operations. And from the bottom, we make the performance and resource of logical qubit and gate by synthesizing hardware performance and error correction schemes. Then finally, we might make this kind of a circuit by performing system synthesis. Then we can show some data about performance. Here, these 3 green boxes are the key components of our method: compiler, system synthesizer, and logical building block synthesizer. So we have developed a chain of software based on the 3 layers. Then I will show some how to develop the layers and what is the key issues in the following. But in the beginning, we are faced with some practical issues because quantum assembly code the list of the quantum instructions. is the size is proportional to the instructions, column instructions. So left side figure shows some conventional column assembly code. Here all the operations are column gate, just gate level. But as I mentioned, our work is focused for large scale. So from the considerations, the column assembly code, the size of column assembly code is so huge. As you see the like figure, for sure 500 bit factoring, we need 39 terabytes file size. So we couldn't even try to compile more largest input case. And based on the large size assembly code, there is another issue. It is difficult to make executable circuit because basically circuit mapping, circuit synthesizing is MP complete problem. So right side, open source. This is an open source compiler raised out of memory error. Even the file size is just 11 kilobyte. So from these problems, we have tried to find some how to make assembly code in small size. We find this modular assembly code approach supported by provided by skepticism compiler from Princeton, UC Santa Barbara, and IBM. So they provide three kinds of assembly code format. The red box is conventional code, all the operations conjugate, but blue box is our target code format. Here there is some hierarchy and some things modularized. This is the example of the quantum module in modular assembly code. It looks like the functions of procedure in classical programming languages. Then how much the modular code can reduce the file size is. Suppose that a quorum function composed of n gate is called n times. Then to describe this situation, the conventional code requires nm gate. But in modular code, n plus n instructions are enough. Therefore, it is possible to reduce the size very dramatically. Back to the graph I have shown previously. Here, for the same size algorithm, we can obtain the very small size column assembly code, actually 10 to the 5 times reduced. So right side is the, upside is the conventional practical code, and low side is modular code. As you see, there is some module hierarchy and something, so there is some information, right? So I think this kind of things can be exploited to optimize later, but not here today. So based on the modular code, we developed the toolchain based on three layers. So I will show some issues and how to develop each layer. In the compile layer, we have applied modification of the step system because we have to apply some circuit optimization techniques. So we modified the step system. And to decompose the RG center gate, we applied grid synthesis and SQCD algorithms. And the target gate is server, particularly the implementable gate. Probably prefer later. And next is logical building block layer. Actually, the detailed operation in this layer depends on the column and control code. I will show first concattenated code case. In this case, we first need to make executable circuit for protocols in computation level 1, and then we increase the computation level for the user demand, I mean the required accuracy based on the algorithm size. The right side table shows the protocols we apply. Actually, in this work, we apply stick code and surface code. Surface code, double defect surface code. So we have to make executable circuit, but somebody may be curious about what is executable circuit. Left side figure, transversal signal. Actually, somebody who is interested in operation have shown so many times the circuit, but in reality, we have to make logical qubit in the two-dimensional lattice layout. Then, in this case, we have to make the signal is done. So here, we have to make the qubits of the same color should be interactive while keeping the fault tolerance. There are more protocols to be made, like the geometry locality concept and keeping the fault tolerance. But then we proposed the method by reviewing by enumerating the characteristics of protocols and develop how to deal with the condition. So we have proposed synthesized algorithms for universal quantum computation, like this one. And our code is uploaded to GitHub. By applying this procedure, we can make protocol in computation level 1, and then we need to increase the computation level for the user demand. So by the techniques, by this slide, we can make computation code circuits, executable circuits. And then the circuits code time. But as you see, the topological code represented by circuits code can be directly quantum circuit if the qubit lattice is provided. In this case, we can find the resource and performance by just analyzing the protocols. So that we calculate or we apply the calculation of code distance like this, and we also cover magic state distillation with these protocols and some vectors. Then now we are ready we can make fault-tolerant logical qubit and gate performance, etc. Then finally, we have to make executable circuit for entire quantum algorithm. So we propose the system synthesis method algorithms for modular assembly code and modular quantum computation architecture. Here, modular quantum computing architecture is something that is combined with computational regions and communication bus. The blue box is example of quantum computational region that is dedicated for certain quantum function from the module in modular quantum code, assembly code. Here, the key point is that, like this one. Actually, suppose again, quantum function composed of n gate is called n times, then the conventional method perform the mapping n times, the making external circuit n times based on the current at that time status of qubit arrangement. But in modular assembly, in this method, we just make circuit just one time, and then we just cite n minus 1 times, refer the n minus time, just copy and paste to the circuit. And here we need some calculation of the code moving distance. We have to find keeping the distance, but in this work we just want to make data, not real external circuit. So it is very simply done. So this graph shows our method is possible. With this our method, very efficient circuit mapping is possible. The lower bars our method and upper bars for conventional method. Actually, our method perform the circuit synthesis within almost 1 hour, but conventional method requires over 1 year. Actually, this is just estimated from the small cases. Okay, so we have, I have described all the key issues in each layer, and then I will show some how items we can measure. The first one is circuit depth. Circuit depth is the length of the longest passive circuit. And next is the fidelity of the entire computation. Actually, this kind of formulas are applied for this job. And then we can find current computation time. Rather than time for just learning once, we find the current computation time to achieve fidelity of 100% by applying these figures, 1 over fidelity. Actually, this shows the required number of iterations. Here, we need to say that we do not consider the probabilistic nature of the algorithm. We just want to make the robust computation, fidelity. So we just want to focus on fidelity. And then we can measure the number of qubits. For that, we first measure the number of logical qubits. In the system synthesis, we can trace the maximum number of logical qubits required at a time, not every phase in the algorithm. And then we can find the total number of physical qubits. It is defined by the number of physical qubits for the logical qubit and the number of logical qubits. Here we also consider the magic state factory capacity, like this one. This kind of formula. Actually, A state for base state and Y state for logical S. And the number of physical qubits for logical qubit depends on the total algorithm code. So left side is our qubit range, logical qubit configuration or the scheme code. The right side is the surface code, logical qubit, in particular double defect based. Actually, yeah, okay. So now I show some result. Actually, please do not focus on the specific data because our work is just methodology, not any data research. We do not focus on the data, and we have not applied any optimization to the best. So we just show some data change trend by applying some as increasing the input size or something. This one is we show some layout effect as the number of circuit because actually we have not optimized the most advanced optimized, but we found that there are so many circuits required. So in case of computation code case, based on the physical error rate 10 to the 9 degree, actually I know this is not physically possible now, but we want to show some comparison between the code and circuit code. So based on this physical error rate, we compare both code. Here, circuit code requires some little resource and better performance. And then we apply some advanced components. In this slide, we assume the physical qubit performances improved. Then the number of resources is reduced. Time is also reduced. Actually, by applying the advanced compile techniques, we show some computation time and resource can be reduced. So we need to develop more advanced circuit optimization techniques. And last, this is the last data. Actually, we may easily guess there is a trade-off between manufacturing cost and fidelity. Right? So, as increasing the computation level and code distance, the fidelity of computation will be improved, but we need more time and qubits. So, in terms of the resource and time, we show there is some optimal level and code distance. So I will conclude my presentation. We have developed software, two types of software for analyzing performance and resource. So we just applied the STEP-CC compiler for large-scale algorithm. We developed some circuit mapping algorithms for computed code, and we also developed the system synthesis method for modular assembly code and modular architecture. So, as I have mentioned, we just developed the methodology, not real data. So we are working on to find some most optimized data now. And this is our team members and my colleagues. Somebody is working on information theory and algorithms and machine learning and sourcing, and somebody working on qubit control and superconducting qubit, and I am working on data pressure and system modeling, and somebody working on compile and circuit optimizations. Okay, that's it. Thank you.
Do you have any questions or comments or complaints? Questions? Okay, then I have a question. Can you explain more of why we should develop the quantum circuit mapping, especially considering the error correction?
Actually, so far there are so many analysis results or something, but underlying circuit or protocol is not executable on the real device. Just a protocol level. So far, 어떤 리포트와 just protocol level, not historical. So there are some optimistic results about for the quantum computation future, but to implement, we have to do something based in the paper protocol, something. So we just want to show them real world. So we need some mapping for algorithm or for logical qubit gate. So to show some real world. So there is some local constraint in the superconducting qubit or something. It's okay. I'm not sure I answered correctly, but to make something.
Okay, thank you. Any other questions? Or thoughts? Could you stand up?
Thank you for your presentation. Regarding on the compiler, you use the SCAPCC. Thank you for your presentation. Regarding on the compiler, we use the SCAPCC. I think they are a little heavy, so there are SCAPs list also released. So do you use both or one of them, and why, please?
Your question is why we use the steps or
So, including that, and SCAPCC and SCAP list, noisy.
yeah.
Do you consider both of them or one of them? And why?
Actually, our target is just large scale fault computation, so we do not consider the skepticism list. Okay, so we have not considered. But as I mentioned, why we consider skepticism is because they provide more compact description about algorithms. Because conventional platinic code generates so huge column assembly code, so practically it is very difficult to manage the code generation or keep the file in storage. So we just use the step system. Actually, but in this case, small case, still the platinic code is useful. So for small case, we just use that. But in this work, and our ultimate goal, skepticism is better to us.
Thank you for your comments.
Any other questions or comments? Okay, then let's do last topic. Let's start to the